Okay, so let's get started. Last lecture we had finished our discussions related to MOS model. Today we start with fabrication and layout. As I said, the analog circuit design is not complete until you make the layout of your circuit, and only once the layout is done do you really know the performance of the circuit, and you can set it then for fabrication as well. Okay, so layout is an essential step for carrying out essential part of analog circuit design. All right, so a little bit of background. I'm not going to go into the details of fabrication. There's a separate course on processing IC technology which covers all of these things in detail. But let me just start with a few simple things. Suppose you have a P-type silicon, right, and you want to create a N plus layer, N plus part, a part of P-type silicon you want to make into N plus here, right? So the way you would do it is, note one thing, there's only a part of P-type silicon which is being made N plus, right? So the way you would do it is, you would take a P-type silicon, you would try and create a window of silicon dioxide here, right? The place where you want to create N plus, you would create a window here. And then what happens is this SiO2 acts as a barrier. And now after that, if you do a diffusion or an ion implantation, the N plus dopant atoms, let's say phosphorus or arsenic, will go only in this particular region. The SiO2 will block the diffusion in these areas, and you will get N plus only in this particular region, right? So what you need to do is create a window in SiO2. Now, how do you create a window in SiO2? Well, you take P-type silicon, you cover it with SiO2 first, right? So it's covered with SiO2. Then, to cover it with, we have to remove SiO2 from a part of the region. So what you do is you cover it with photoresist. You cover it with photoresist, and then you have a mask. The mask is nothing but patterns of a set of geometrical drawings. Some opaque regions are there, and some transparent regions are there. So you have a mask, and then you expose it to UV light. So what happens is the dark portions do not allow light to pass through, and the transparent portion would allow the light to pass through. And the nature of the photoresist gets altered once it is exposed to. It's a photoresist. It's an organic compound which is sensitive to light. So its properties change here. And then what you do is, after that, you develop this particular photoresist. You end up removing the photoresist from a part which has been exposed. And once you do that, then you can take hydrofluoric acid and etch the silicon dioxide here, right? And then you remove the photoresist. And thereby, you end up getting the window and SiO2 that you have, right? So you're seeing that it requires a sequence of processing steps. Where does a designer come into picture? As a designer, circuit designer, of course, you're not going to etch SiO2. You're not going to remove the photoresist. That's what happens in a foundry, in an IC foundry. They will do all the steps for you. Where do you come into picture? Here. All that you have to do is specify that I want N plus in this particular region. Once you specify this particular drawing on a mask, then with that drawing, let's say this is an N plus mask, right, which tells you where you want N plus. Once you do that, then the foundry, people at the foundry can do all the sequence of processing steps and give you an N plus region. So that's where you come in, because at the foundry, they don't know whether you want an N plus here, or you want it here, or here, and of what dimension. These are the things that you need to supply. Okay? So basically, mask design is where you come in. And in order to understand what are the different masks that I have to design, I need to understand the outline of the fabrication. Okay? So that's what we'll do. So what we are interested in is, in the beginning, how to create an N-type MOSFET here and a P-type MOSFET. And as I've just said, fabrication in a simplified view is transfer of pattern from the mask to the photoresist. We call this step as photolithography. Once we get it onto photoresist, we have to transfer the pattern, whatever pattern you want, to the silicon, right? And then once you transfer it to the silicon, and then a sequence of processing steps. You have diffusion, annealing, all kinds of things that are there, right? So this is where we come in, design of mask. All right, so with that background, let's start with the different masks that are required for fabrication of a N-type and a P-type MOSFET. This drawing, I'm just illustrate a couple of things here. What you see here is a N-type MOSFET. This region in this green is N plus here, and red is where you see pollen. So that's an N plus N type MOSFET here. This is a P type MOSFET here. All right. For the N type MOSFET, the body contact is not shown here. For the P type contact, these are P plus region here, P plus and P plus here, and this is a contact to the N type here, N well. This is the N type N well here, in which the P type MOSFET is being fabricated, and there's a contact to the body as well. Now, note one thing, that on the surface of the silicon, there are regions which we call as active areas. This is an active area because I'm making the active device there, the transistor there. That's an active area. This is again an active area. Rest of the area is all covered with, this is silicon dioxide. Rest of the area is covered with silicon dioxide. So there are active areas where you're going to make your transistors or resistors or capacitors or whatever. Those are the active areas. And all the rest of the region is, this is silicon dioxide here, this is silicon dioxide. Not only that, the entire transistor, this yellow region that you see here, the entire transistor is covered with silicon dioxide. The whole thing is covered with silicon dioxide. Okay? And then these are what you see here, these are the contacts that are being made here. So contacts are made by sort of drilling holes into the silicon dioxide. So this is a hole into the silicon dioxide that has been drilled. And this is a metal layer here, which makes a contact here. So this is how you are making a contact. If you want to connect two terminals, you can see here, a contact is being made to the source here, and a contact is being made to the body here, and this metal is shorted together, and therefore the source and body get shorted. Okay, so keep that in mind, that there is an active area where we make the transistor, and the rest of the region is all covered with silicon dioxide. The reason is, you can see that I want, for example, isolation between one transistor and the other. If, for example, I didn't have this, then there's a possibility of contact between the two. Okay, so it's for the purpose of isolation here. And the whole thing is covered with silicon dioxide, and you make contacts here. This is one level of metal. What can happen is, for example, one layer of metal may not be enough to connect all of them. So you can cover this on top. I'll show you later on with another layer of silicon dioxide. And on top of silicon dioxide, you have second layer of metal. And like that, you can have 5, 6, 7, 8 different layers of metal. Okay, so keep this picture in mind, and then let's start here. All right, so fabrication process begins with silicon substrate. We are assuming that it is a P-type with an epi layer here. Doping depends on the technology that one is using. Maybe 10 per 15, 10 per 16. The doping is there. Typical wafer size that we are using is 300 mm right now, and the thickness is around 700, 800 micron, the thickness of the wafer. Okay, all the devices that you are made is maybe in the top 1 micron. The rest of the wafer is simply used for support. You have a 12-inch size wafer, and all that thickness that you see here is to provide mechanical support. You make everything on the top layer of the silicon wafer. All right, so remember, we are going to make both P-type and N-type transistors, right? So for P-type, keep in mind that I have a P-type substrate, so N MOSFET I can make directly on it, but for P-type I have to create an N-well. So that's the first thing I'm doing here. I'm creating an N-well. This is a cross-sectional diagram here, which shows an N-well, and this is the top view, right? Top view, which shows that in this part of this thing, I'm going to create an N-well. Now note, N-well is made selectively. It's not that you're making N-well everywhere, so I need a mask here. I need one mask which will define where the N-well is going to be there, right? And the dimensions of that particular well will tell, I have to specify what is the dimension here, what is the dimension here, as a design, okay? Next thing is, after you have a N-well, define which are the active areas. Active areas. Now, what I'm showing here, if you look at the cross-section, that there's an active area, and this shaded region that you see is silicon dioxide. Right? So anything outside the active area is all silicon dioxide. It's all covered with silicon dioxide here. So this is an active area, this is an active area. And I'm showing it here as a top view. Top view. So you need an active mask, right? To specify, again, where you're going to make different transistors here. Now deliberately, see, this is where I'm going to make, in this part, NMOS. And this another one, I've deliberately shown slightly away. I'm going to make a contact to the body. I could have merged the two together also as one large active area mask, and I could have made a contact to the body right here. But deliberately I made it separate. So body is a little bit away. Similarly, body contact is a little bit away. So here, this is for the body contact, and this is for, so this is the end well. In this active area, I'm going to put P plus, gate, and all of that. I'll make a transistor, and here is where I'm going to make a body contact. Okay, so that's why it's separate. Okay, so let's, next thing that I do is, once I define the active mask, I define the gate. Gate is defined first. So gate is defined by poly. Now, what has been done is the surface has been covered with a very thin gate oxide, and on top of gate oxide you deposit poly, and then you pattern it, and create poly at the regions that you want. So this is where the gate is. The red that you see is the poly here, and so this is where my gate is as a top view. I have two gates here. This is for the N type, and this is for the P mask. So I need a poly mask. How many masks do we have right now? We have an N-well mask, we have an active mask, we have a poly mask. Next, what we do is we create N diffusion or N implantation, right? So what we do is we cover up those areas where we don't want N diffusion. So we cover up this area here, and then we diffuse or we implant, right? So we get, we cover up this area, so we get diffusion here and here, or implantation here and here. So we get N plus region here, and we get N plus here. Remember, the body contact with the PMOS is also N plus, because the well is N, so the body contact is also N plus here, right? So we have created N plus region. So we need one more mask for this one. Next, similarly, we'll create P plus region there. So we need a mask here. We create node here, P plus here. These are source and drain, and this P plus is contact to the body. Okay, and so we need a N select mask. Next, we're going to make contacts. So as I said, now the transistors are complete now. Once I do N plus and P plus, transistors have been made. Now what we do is we cover the whole surface with silicon dioxide. You can see here, this whole thing is covered with silicon dioxide. All the transistors are covered with silicon dioxide. And then contact cut mask means I drill holes through the silicon dioxide. I drill a hole here and I fill it up with metal, right? So you fill it up with metal, it's making a contact here. You fill it up with metal and it makes a contact here. And this is what these small squares that you see here, these are the places where we have made contact. Contact to all the layers that you see here. We have made contact here. I've not shown you have to make a contact to the poly as well. And you have to make contact to whichever other layers are there, right? So these black squares that you see are contacts. Next is, once I make a contact, I may want to connect certain terminals. So I have a layer of metal here that you see, which is connecting, let's say, the drain of NMOS to the drain of PMOS here. So it's connecting it up together. So I have a metal one, and so everywhere I need a mask, right? I need a mask for the contacts. I need a mask for the metal one, because metal one is here and here, it's not there at this breadth. So whenever you have to do things selectively, you need a mask, right? And you have to specify what the nature of the drawings on the mask are. And this is the top view. You can see that we have connected up the drain of this transistor and the drain of this particular transistor here. Now, as I said, one layer of metal may not be enough to connect up all the transistors. So what you do is, this is what we call as metal one, as you can see here. What you do is you cover this whole thing by another silicon dioxide, right? Another layer of silicon dioxide. And on top of silicon dioxide, you have a second layer of metal. But then how will you connect second layer of metal to the first layer of metal? You again need to drill holes there. We call it via. So via mask. So you need via mask to connect metal 2 to metal 1. All right. And via mask. And then you will need a metal 2 mask here. So this is the picture that I was talking about. You have these multiple layers of metal here. This is metal 1. This is metal 2 and metal 3 and metal 4 and metal 5 and so on and so forth. And, in modern technologies, you may have 8 or 10 layers of metal. 8 or 10 layers of metal stacked one on top of another here. And in between two levels of metal is basically an insulator. It could be silicon dioxide, it could be other insulators as well. And note that how they're connected. So you need a via mask to connect metal 2 to metal 1, you need a via mask. Similarly, if you have 3 layers of metal, then I require a metal 1 mask, I require a via mask here, I require a metal 2 mask, I require another via mask, and I require a metal 3 mask. So like that, depending on how many layers of metal are there, you require via an appropriate metal masks. So that's how you end up. This is in brief how you end up fabricating the NMOS and the PMOS. And you can see here that you need, if you have a two layers of metal in the simplified process that I've shown you, you need at least 9 masks that are there, right? And so if you have to specify a layout now, you have to do drawings for all these nine masks. Okay. All right. So let's now while one is doing so this generation of layout, another word that we use is physical design. Now, physical design, as I said, is a set of geometrical drawings that you have to do, which specifies where you want N plus and poly and things like that. Now, while you're doing it, you have to obey certain rules. You can't have any shape, you can't have any spacings. There are certain rules that you have to obey, which we call as design rules. And these rules have basically been made such that when you make a circuit using that particular layout, the circuit will work without errors and will give you reasonable yield. Okay, yield meaning that if you make 100 ICs, at least 80% or 90% will work. Okay, so keeping in mind the yield constraints and the errors, these rules have been made. And let me illustrate some of those rules here. Okay. Now, what I'm going to do is specify rules in terms of a parameter called lambda. All rules will be specified in terms of, we'll say 2 lambda, 3 lambda, and 4 lambda. What is lambda? Well, the definition of lambda is as follows. If I have a technology which I say is 1 micron technology, then the corresponding lambda is 0.5 micron. If I have a 2 micron technology, the corresponding lambda is 1 micron. So keep that in mind. What do I mean by 1 micron process? 1 micron process means is the minimum dimension that I'll be able to get through the technology. Minimum dimension. All right. So minimum dimension that you can get is 2 lambda, right? Because if it's 1 micron process, lambda is 0.5 micron. So minimum dimension that you can get anywhere is basically 2 lambda. All right. So I'm going to specify rules in terms of, these are called lambda rules. Okay. So let's see some of the rules here. For example, this is a well here. Remember N well, there could be a P well also. So what it says is if you have 2 wells, first of all, what it says is the dimension of the well has to be larger than 10 lambda. That's the rule. You can't make a well less than 10 lambda. You can, all these rules specify minimum values. You can make larger. Nobody's stopping you. So you can make a well 20 lambda, 30 lambda, whatever you want. But minimum it says is 10 lambda. Then it says, if you have 2 wells, which let's say are at different potential, then minimum spacing between 2 wells has to be 9 lambda. Which means that if you want 2 wells to be isolated from each other, keep the spacing at least 9 lambda. These are the active regions where you make the transistor. It says the minimum dimension here is 3. What actually it is specifying is that N plus layer that you see there, the minimum dimension of an N plus layer is 3 lambda. Minimum separation between 2 N plus layers is also 3 lambda. This is poly. Poly is what you use for defining gate. It says minimum dimension of a poly is 2 lambda. And the separation between 2 poly layers also has to be 2 lambda. Similarly, specifies for metal, minimum dimension for a metal 1 is 3 lambda. Spacing between 2 metal lines is also 3 lambda. It says the contacts that you make, they're all 2 lambda by 2 lambda. Okay? Contacts are 2 lambda by 2 lambda. This shows you, these are some more rules. It's showing you a transistor. This is a N plus region. This is also an N plus region. And this red that you see here is a poly. Right? This is a gate, and this could be the source, and this could be the drain. Right? Now it's telling you several rules. It's telling you that, and let's say this is made, there is a well boundary. It could be a N well boundary. So it says that this active region that you see here, this N plus, all that N plus region here, it has to be at least 5 lambda away from the well boundary. N well, for example, is there somewhere in your layout. This has to be away at least 5 lambda. 5 lambda here. It says that, for example, the N plus layer that you see here must extend beyond the poly here by at least 3 lambda. If it extends by only 2 lambda, the manufacturer is telling you that maybe the transistor will work, but maybe you will not get enough E. Why you will not get yield, we'll explain in a minute, because the manufacturing process is not perfect. So when you are saying 3 lambda here, when a manufacturer is going to make these layers, it may happen that this layer may go a little bit up above or a little bit below, right? So you have to keep certain margins in mind in order to ensure that this n plus layer extends beyond the poly layer here. Then only you get a transistor. Then only you have a drain and a source, and you get a transistor. Otherwise you won't. Similarly, it says that poly layer here must extend beyond the n plus by at least 2 lambda. Right? It must extend beyond by 2 lambda. And similarly, there are other rules. There are various rules here.
This is the top view.
This is the top view.
So why is the poly extended in the other shape?
Why is the poly extended here or here? That side, because I may want to connect it to something else.
Like when you say the distance should be 5 lambda from the wall.
From the end well.
Yeah. So is it from all the sides?
From all the sides, yes. All these n plus have to be away from the well by 5 lambda. What it's saying is, 5 lambda from the well edge, right? Again, these are the rules that I'll give it to you, and once you start doing layout, you'll have to become familiar, and so there are rules regarding the contact. Let me see. So contacts, these are, for example, contacts being made to the poly, contacts being made to metal 1, contacts being made to metal 2. So these are rules, as I said, you'll become familiar as you do the layout. Okay, there are more rules here specified. All right. I just want to quickly illustrate where these rules are coming from. Okay, so as an example, we know the basic idea is that the fabrication process is not perfect. That's one reason. And then there are other electrical and reliability reasons because of which you have to ensure that certain minimum spacing is there. Now, let me illustrate that as some of these points through this particular example. Suppose you want to create 2 n plus regions, right? 2 n plus regions are there. And there's a rule which says that the 2 n plus regions, there has to be a minimum spacing of, let's say, 3 lambda. Now, you may ask, why should there be a minimum spacing of 3 lambda? Why can't I just bring them very, very close to each other? All right? I have 2 n plus layers. These 2 n plus layers have to be isolated from each other. Why can't I bring it very, very close? What will happen? Well, if you bring very, very close together, you can understand, because the fabrication process is not perfect. It may happen that this may get displaced to the right, this may get displaced to the left, and the two may overlap. So you have to prevent that, right? And then there are other reasons as well. For example, you know that this is an n plus layer and this is p type, right? If you have an n plus and a p type, what do you have around that? You have a depletion region, right? So there's a depletion region around it, and there's a depletion region around it. If you bring them too close to each other, what will happen to the two depletion regions? They'll overlap, they'll merge, and the moment they merge, it means that they're electrically connected with each other. Right? So it's not just the errors in the fabrication process which tell you that you have to keep minimum spacing, but it's also, for example, as I said, there are electrical reasons. I don't want this to get coupled to this one. Right? So the next slide actually tells you the different kinds of errors that one gets here. For example, you have a mask which tells you that you want to create n plus in this region and this region. When a light goes through the mask, you have diffraction. So the light a little bit spills out, right? So it may or may not be very important. Finally, all right, so you expose a region which is a little bit larger than the transparent region because of diffraction. Then, when you expose it, then as I said, you have a photoresist. So you have to remove the photoresist. Now, when you remove the photoresist, the removal process or the etching process is not vertical. It goes a little bit sideways, right? Similarly, when you etch the silicon dioxide to create the window, the silicon dioxide doesn't get etched vertically. It may spill over. So what happens is, you wanted a spacing of this much, and look what the spacing has become. Because of all the flaws in the fabrication process, the spacing has become larger. And the two n plus regions then have come closer together. Now when you diffuse, or implant, it's not that n plus is only in this region here, n plus goes underneath the oxide also. As you implant and you anneal, the atoms diffuse, and so you get n plus under this and under this here. So note that you started with so much spacing between the two n plus layer in your mask. Finally, you end up with an n plus layer spacing which is so small. And then, as I said, the depletion regions are there. And if the spacing becomes too small, either the two n plus regions may overlap, or the depletion regions may overlap and you don't get two isolated N plus layers. So this is why it is telling you is that you have to maintain a certain spacing. And the manufacturer of that particular technology has figured out all those, how small can the spacing be, and still all your devices will work properly. So that's where the rules are coming from. So when he says 3 lambda, 2 lambda and all that, it is coming from all those manufacturing errors and keeping all the depletion regions apart and all of those things that are there. So the rules are coming from there. Okay, so what I'm going to do is just step by step illustrate for you how layout is done. Okay, layout for a CMOS inverter, and this is also an amplifier. If I apply a biasing voltage and then apply a sinusoid, this can also act as an amplifier. So your CMOS inverter is also one of the simplest CMOS amplifiers that you can have. Okay, so let's start and do the layout of this particular transistor here. This particular inverter or amplifier here. Note the dimensions. Dimensions is 3 lambda by 2 lambda, which 2 lambda means the length of the N-type transistor is 2 lambda. Everything is now specified in terms of lambda, right? So it's 2 lambda, the width is 3 lambda, 2 lambda here and 6 lambda here, right? And this, I have to connect it to VDD, to ground, V out, V in. Okay, so let's start. Oh, okay. So the first thing that we'll do is make the NMOS. Does everybody see this is an NMOS transistor? Now, as a designer, we are not, we don't specify all the things. The critical things is what we specify. The rest of the information, it can be automatically generated. All right. So, for example, when I draw something like this, it becomes a transistor. How? I'm saying this is the region where I'm going to do N plus, right? N plus here, and this is the region where I'm going to put poly. So if I have a poly here, it's understood that underneath poly there's a thin oxide. Okay, and N plus is only in this region, and N plus is only in this region. Okay, so you get a source here and a drain here, and you have a transistor. NMOS is ready. It requires only 2 drawings here, and we use colors to denote the layers here. So all N plus that you will see here will usually be green. Poly will be red. And note the rules that I use. You can see here 2 lambda. So this defines the length of the transistor. Note the transistor action is from source to drain. So this is length, 2 lambda. And then there's a rule which says that the minimum dimension of anyway this N plus has to be 3. And in our case is 3 anyway. So it's 3 lambda. Okay. So that's the transistor. What is now my active region is wherever you see this N plus region is where my active region is. Everything outside is what? Silicon dioxide. Remember, everything outside is silicon dioxide here. So this little poly that you see here outside, this little poly is also over silicon dioxide. Active area is only this rectangle here, this green rectangle that you see. That's the active area. Okay, everything outside is silicon dioxide. All right, so this extra poly is also over silicon dioxide. But poly inside is over what? Is over gate oxide. Please remember, there are 2 different kinds of oxide. Inside the transistor, there's a very, very thin gate oxide. Right? So poly here is over a thin gate oxide. This is where transistor is being formed. Poly outside is over a thick oxide. Okay, it's for isolation purpose. All right. So that's my transistor N-type. Now I have to make a contact. I have to make a contact. Now contact I'm making through a metal, right? Metal, and which is connected to ground. So see how I'm making the contact. Look at the drawing. So what I've done is there is a layer that I've drawn. Blue denotes metal 1. So there's a layer here that I've drawn which is a metal 1, right? Layer of metal. And there what I've also put is N plus here. See, to make a contact, the metal and the N plus have to overlap. If there's no overlap, then you can't make a contact here, right? So there's an N plus here, layer here, and there's a metal also here. Both are there. N plus and metal both are there. And then there's a contact also that you see there. So to make a contact, you need N plus, you need metal, and you need a contact also, that hole also there. And that's how you make a contact. So that's where the contact is being made. And there are design rules which tell you that the contact dimension has to be 2 lambda by 2 lambda. That black region that you see here, Has to be 2 lambda by 2 lambda. And there's a rule which says that this black region, the contact has to be surrounded by N plus and metal by at least 1 lambda here, that you see. 1 here, 1 here, 1 here. It has to be surrounded. If it's not surrounded, then errors will crop up. Okay, so this thing is there. So now what I've done is, I have an NMOS transistor. The source has been connected to ground. I'm going to call this particular metal here as ground. Right? Okay, so NMOS is complete and a contact has also been made. Now I'm going to make the substrate contact, body contact for the NMOS. Okay, so remember, body is here. Now body is of which material? Body is p-type. P-type, right? So I look at that now. Physically I'm making a body here. You see that here? P-type. This orange is what I'm going to use for P. Now I'm making a contact also. So now note, it's not shown in this particular diagram. This square that you see here, I have a P plus layer here. Underneath or on top of this P plus layer is also a metal. I have not shown. There's a metal also. So when I draw this blue region, metal 1 mass, the blue region is like this here, and then it will come down and like this. Okay? That's where the whole metal is. I have a metal and I have a P plus region, and then I have a contact. That's how I make a contact. Okay? So to make a contact, remember when I say I'm making a contact to the body, what am I saying? I'm making a contact to the body, from the body to the metal. The contact is between two layers. And what are the 2 layers? A P plus layer and a metal layer. And in between is the contact. That's how I'm making a contact. Alright? And so now note, is the same metal that I've extended all the way here. Right? So I've shorted the body to the source. Body is shorted to the source. If I didn't want to short the body to the source, then what I would have done is maybe extended this region somewhere below and have used a separate layer of metal. Then you wouldn't have shorted. But right now is the same metal which has been extended here. Alright. So whenever I draw something like this, it's understood that the metal is also there, although I'm not showing it explicitly. Okay. So body contact is also been made. Next, note now on top of that I have a PMOS. So the drain of NMOS has to be connected to the drain of PMOS. And how do I connect? The drain of NMOS is N-type. The drain of PMOS is P-type. So how do I connect the two? Through a metal. Right? So that's what I do now. So this is what I'm showing. So first what I have to do is that N plus layer here, I have to connect it to the metal. And then this metal will be going upwards here. So this is what I do here. Note here. Now, again, you don't see it, but there is a metal here also. In the big square that you see, there is a metal, and there is an N plus, and there is a contact. And that's how you form the contact. And you have to keep in mind all the rules that are there. So this is about 4 lambda. So now this metal I've extended because I'm going to connect a PMOS on top. Okay. So now I have all this part ready. Right. So I have a body contact, I have my source, I have my drain, and then there is a contact here. Alright. Now PMOS is fabricated in an N well. Right. And we have a rule, as I said, design rule dictates that the well boundary must be away from all active regions by at least 5 lambda. So what I do is, this is where I draw my N well edge, because it has to be away from the active region. This is an active region by at least 5 lambda. So this is where my P well or N well boundary is. Right. So I have to make my PMOS on top of it here, inside the N well. Okay. And of course I have to connect my N type to P type here, so I'm extending the metal also. Okay. Now this is where I make the P-type MOSFET. P-type MOSFET is this P plus here, and this poly is here, and I've connected to VDD also, metal. So you can see this will be my, let's say, drain, this will be my source, and source is connected to VDD. The contacts have been made here. And this has been made at least 5 lambda away from the well boundary again. Right? So you have to extend 5 lambda here. And you know, once we draw the whole well, it has to be away from all of this by 5 lambda, from the P plus regions. Okay, so I've made a contact now to the VDD, and I've made a contact here. So the two have been connected together. What else is missing? This is now the P well, N well boundary. I can draw the N well now. It's all 5 lambda away here. Now there's a rule which says if it is N well, and now by the way, I've also added a Body contact. Body contact for P-type MOSFET is N plus layer. Okay, so I've put an N plus layer here, and I put here, now note again, metal is not explicitly shown here, but there's a metal here also. There's a metal on top of this N plus layer also. It's not shown, and so you've shorted the body and the source contact together. Right? And we have an N well also. Now all that we need to do is connect the two gates together. Now I have one option of, please keep in mind that poly is also conductive. It's a heavily doped poly. So for short interconnections, what I can do is I can take this poly and directly connect it. But if it's a long interconnect, then what you do is make a contact to the poly using a metal, and then take this metal, bring it down here, and then make a contact again. Alright, so for example, now this is what I've done. I've used the poly itself as an interconnect. The same poly, I've taken it here, comes out here, and makes a contact here. The two polys are shorted together because the two gates are shorted together. And then at this point, I've connected poly to the metal. Poly has been connected to the metal. Now, if there is another inverter, I can easily connect another inverter by directly connecting the two metals together. So now this basically completes our layout. A full layout has been done where I have an NMOS, I have a PMOS, the two gates are connected together. I have a body contact here, it's connected to VDD, connected to ground. Right? So the whole inverter is, or an amplifier is ready for you. Now, of course, after doing the layout, if the layout has been correctly done, there are a couple of things that one has to do. In a software, for example, once you do the layout, software, for example, when you do the layout, it will constantly tell you whether you are violating the rules or not. You know, anytime you violate the rules, interactively it will tell you by showing some hashed region that some rule you're violating. And if you click, it will tell you which rule you're violating. So you can immediately correct. Right? But anyway, so after doing the layout, what we do is something called DRC, design rule checking. So there's a specialized software which will check your design for all the violations of rules. And if none of the rules are violated, then the design passes through the first stage. Now, after having done this layout, are you ready to ship it to the foundry or what? It doesn't violate any rules. What should you do? Huh? It doesn't violate any rules. You made the right connections or not. So what we do is there's a step called from the so what you would be doing is you would have a schematic in front of you, right? And from a schematic you're drawing the layout. So from schematic to layout you have done. Now design rule checking will not catch the fact that you have not connected the two polys together. There's no violation of rule if I just leave two polys hanging. Right? It will not catch. But then it denotes that you have not faithfully translated the schematic into a layout. So what we do is from the layout, there's a CAD tool which exists. What it does is it looks from the layout, it extracts a schematic, new schematic. Okay, from the layout, it extracts a new schematic. Right? And now this new schematic can be compared with the old schematic to check whether all the connections and all that have been done properly. This is what we call as layout versus schematic check. So there's a tool called LVS, layout versus schematic check tool. So that will automatically extract your schematic and check. So suppose you automatically extract and check and it passes that. Are you ready to send it? There are no design rule errors. You've compared with your schematic, it matches with the schematic. Are you ready to send? Is your design complete? Or there's something remaining?
I want to do a simulation and check if the circuit works.
No, so you've already done the simulation of you've designed the circuit, you've simulated it, right? And now you're doing the layout. And you know now that you've done the layout properly. Why should you simulate again? Huh? Circuit what?
You should simulate it because the W/L ratios are correct.
No, it checks. It will check that.
The layout.
Yeah, it will check the W/L and all that. Yes, it will check that. Transistor sizes are easily checked. You know, you can easily extract what the transistor size is. Very important part is capacitances. When I talked about capacitances, say drain to body capacitance. What does it require? Drain to body capacitance, what does it require? Area of the drain, perimeter of the drain. At the schematic level, do you have information of the area of the drain, perimeter of the drain? Now you have. Now you know where is your drain. See, this is the drain here. This region here is the drain. Now you have information about the area drain and perimeter drain. This is this drain part here, this one here. At the schematic level, what information did we have? Only 3 lambda by 2 lambda. What is that information? Only this one here. Remember this 3 lambda and 2 lambda. You don't have information about area drain and perimeter drain. So what we do is we do a layout analysis. So as part of schematic versus LVS, layout versus schematic check, what the tool will do now is, while it is extracting all the transistors and everything, it extracts all the areas. The tool will now, from looking at this, your circuit will tell you the area of the drain of transistor M1 is so much. Perimeter of the drain of transistor M1 is so much. And that information is now extracted. With that information, we now calculate all the capacitances properly. And now once we have all the capacitances properly, now I have to simulate again. Now only I have a real assessment of the performance of my circuit. Because remember, earlier simulation that you have done, this area drain, perimeter drain, and many of the parasitics are not there. You don't have a good assessment of the frequency response or the transient response. Because many of the key capacitances are not there or they're not properly modeled. It's only after you do the layout that you have an assessment of capacitance and you have to redo the simulation. Once you do the simulation and it passes all your specifications, now I would say you're ready to send it off. Okay? So the steps are, you do a schematic design, you do a layout, from the layout extract the schematic back, verify that the two schematics match, and then redo the simulation of the schematic. If it satisfies all your specs, your layout is finally ready, and now this layout can be converted into a format. There are different formats which are there. It's basically like a data file. You can convert the whole thing into a data file and email it to the foundry, and they'll make the masks, and then they'll make your ICs, and then after a while, after a few months, you'll get the ICs. Okay? So what we need to do is, the task is not complete. We need to analyze the layout. All right. So the first thing that we analyze is important. What is the area? Now, how do I determine the area? What I do is I draw a rectangular box which completely encloses my layout. Minimum size rectangular box which completely encloses my layout. In this case, keeping in mind all the rules and all that, the width is 15 lambda, the height is 45 lambda. So the overall size of my inverter or amplifier is 675 lambda square. That's an important piece of information in a layout. What is the size? The other thing that people are interested in is aspect ratio. So this is aspect ratio. The height versus width is 3:1 here. Aspect ratio, you will see later on the aspect ratio, why it is important. Then, as I said, we need all this information. What is the drain area? What is the perimeter? So I can manually go and look at it here. This green region that you see here, all this green region, I look at this area. You can calculate from the dimensions given, 19 lambda square. And the perimeter, again, go all around the boundary. You get 15 lambda. Similarly, PMOS drain area and perimeter. So that's another information that you get here. So that's there. For parasitics, if you look at this poly here, right? So poly that you see here, as I said, all the poly which is outside the active region is running on top of silicon dioxide. And I need that area also, all this poly that you see here, all this red here, outside the transistor area. Its area is around 80 lambda square. And there's a capacitance associated with that wire, that poly wire. Because remember, this poly is conducting and it is on top of silicon dioxide. So there's a capacitance associated with it. This one, similarly, you see that there's a metal region here, right? Look at this metal region here. This metal here. This metal, where is it running? Metal one is also on top of silicon dioxide. So it also contributes to a capacitance here. So I need a metal one area. Metal 1 area is about 60 lambda square. Its perimeter is 26 lambda. So all these things are evaluated. Different areas that you see here, areas and perimeters are evaluated. These are all used to calculate all the capacitances that are there. Okay, let me give you an example. The capacitance that you see here, the gate capacitance inside the, before that, if I go back and look at this layout, what was the size here? 3 lambda by 2 lambda. So if you didn't do a layout, you would have said the area of that particular transistor how much? 3 into 2, 6 lambda square. And this one was 6 lambda by 2 lambda. So area was 12. 12 plus 6, 18 lambda square, right? If you just look at it, you would say the area of my inverter is 18 lambda square. How much is the area? Look at that. 675 lambda square. Right? So area of your final area that you have, this is a very small area that you see here. Right? The actual transistor area is very small here. This is the only transistor area. The N plus source, the N plus source, drain, body, metal, all these things that take up the major area. So when you look at the area of the circuit, it's not simply counting what is the area of the gate. And that's where people make a lot of mistakes. For example, suppose I add one more transistor. Now, will the area double? It may not. All right. So the point that I'm trying to emphasize here is that it's not a very simple correlation that if I'm adding more transistors, if I double the number of transistors, the area also will double. That's not really true. Of course, as you add more transistors, the area increases. That is obvious. But it's not that it doubles. So one cannot simply count the number of transistors and say, one circuit has twice the number of transistors than the other, and therefore its area is double. That's not true. Okay. So keep that in mind. There's a huge difference between this area and the area that you just saw. Okay. What I wanted to show was capacitances here. So now remember, this is an inverter or an amplifier. If I start looking at a signal which is coming from here, from the input side, what is the capacitance that it sees? Input capacitance, right? So of course, one is the capacitance of the transistor here, gate, right? And the transistor of the gate here. But there are other capacitances also. And there's a capacitance due to all this poly line here that you see, poly wire outside here, all this thing here, and there's a metal here. And therefore, let me show you what the capacitances are. Here, what I've done is, I've taken two inverters connected to each other. Right? The output of this one is connected to the input of the other. Okay? And specifically, what I'm looking at is, what is the capacitive load here, right, at this particular point, here, in between. Okay? And so I can calculate by looking at all the wires and everything, I can calculate here. Capacitances will, at this point, will come due to this part of the N-type MOSFET, the gate of the P-type MOSFET, plus all the parasitics here. Okay? Don't worry about all of this. Let me show you what it is. So the total capacitance at this point is 12.1 femtofarad, out of which 1.1 femtofarad is due to all these poly and parasitics, which is not due to the device. It's due to the interconnect wires. Even in a very, very simple, compact layout, 1.1 femtofarad out of 12 femtofarad is due to all, which parasitics? All this blue metal that you see and this red poly and all that. It contributes to at least 1 femtofarad. So you have about, if you neglect this here, you have about at least 8 or 9% error here, 1.1 femtofarad. Okay, it's a fairly significant one. So even in a very simple layout, interconnects are an issue. If you have a wire, if let's say this is inverter 1 and this is inverter 2, I connect it with a long wire, 100 micron. Then of course the capacitance due to the interconnect itself is 11 femtofarad. So the point is, here I've just connected the two inverters, just put them adjacent to each other. But suppose I had a wire here, long wire here. This wire itself would have given you 11.5 femtofarad. Okay, so that's another reason why assessment of performance at the schematic level is not correct, because I don't have any assessment about the wires. How long are the wires? What are the capacitances associated with the wires? Those things become available only after you do the layout. The wire capacitances, all the parasitic capacitances. Okay. All right. Here is a question for you. Identify the layout. What is this layout for? Well, you can draw it out, sketch it out. What is this circuit?
What are the pink wires?
Huh?
Pink,
Okay, so this is the red one is poly. Where the metal and the poly connect with each other, it becomes pink. Now here they're showing there's an alteration of color, so a contact is being made here. Okay, this is the ground here. So all this region that you see here is a green region with a poly here, and there's a well here. There's a well here, and this one is a P plus here, and there's a poly here. There's a P plus region here. Okay, P plus is they've used a slightly different color here. So P plus here, and then there's a poly here. Okay. So what is this circuit? And the blue region that you see here, all this blue region is overlapping the green region, and there are a lot of contacts being made. So there's an NMOS here, there's a PMOS here. Can you see NMOS here? That everybody can see? PMOS? PMOS is also here. There's a poly here, and as I said, there's a P plus here. So poly here. And what is being done to the poly and there's a metal which is connecting the two. And the poly is connected back here. Which means gate and drain. Gate and drain are being shorted together. Source is connected to VDD. Source here is connected to ground. So this is what I have here. Right? This is what I have here. This is my M1. This side is source. This side is drain. And the drain is connected through the metal here that you see. And this is connected to the M2. M2 source is here. I don't know source and drain here. I have to identify it. But when I know VDD here, then VDD is closest to the source of the PMOS here and drain here, and I can see them shorted together. Now, something interesting you see here. NMOS is a very wide NMOS. It's a very wide NMOS, deliberately because I make it very wide, because transconductance depends on the width. So I make transconductance large because gain depends on transconductance. So I made transconductance large here, alright? So that's why the width of the transistor has been made large. Why do I need these multiple contacts? Well, look at this one here.
How do you decide which is drain and which is source?
No, you don't. As far as MOSFET is concerned, drain and source are interchangeable. So it depends on your circuit, on your schematic, what you have done.
So like in this one also?
In this one, for example, anyone can be, but it's specified that this one is ground. And so ground would be closer to the source rather than the drain. Okay, so that becomes the source terminal. Now, look at this thing. When you have a very wide source, very wide transistor, I could have done the following. This is my N plus region here. I could have just made one contact here and connected it here. Right? I could have done that. Logically, there's nothing wrong. But remember what is happening. This is source and this is drain. So current is flowing like this, like this, like this, right? So imagine current flowing, electrons flowing here, and then they have to flow up and then go here. Right? Now, as they go here, this is where the transistor action is, going from source to drain. But going from here to here is what? It's simply resistance. It's simply a resistance. I don't want a resistance in my transistor. Right? So although I can make a contact only here, but then this current flow now sees this extra resistance. And this resistance is detrimental. In fact, it reduces, you can very easily calculate if you take a transistor and put a small resistance in the source, the effective transconductance decreases. Okay? So I don't want that, and that's the reason why we have made contacts at all these points. So in your source and drain, make as many contacts as you can accommodate. depending on the width of it. Here one has 1, 2, 3, 4, 5 of them. Here there's no space, one is enough. All right. So put as many contacts as you can accommodate in your source controller in order to make the resistance associated with those terminals as small as possible. Okay. So that's why you see all these things. All right. Let me come back to design rules. Now, design rules that I've just talked about are what I call as lambda rules. Now, lambda rules, of course, have an advantage. 2 lambda, 3 lambda, these are very easy to remember. Very easy to remember and very easy to carry out design. All right. Instead of, suppose I had a 0.18 micron technology and you have to remember this is 0.118, this is 0.36, this is 0.54 and all that. That's more difficult than simply 2 lambda, 3 lambda, 5 lambda. Okay. So one advantage, of course, is very easy to remember. And therefore easy to carry out design here. But a more important aspect of lambda rules is it gives you a technology independent layout. Technology independent layout. Can you see that? As I said, if I have a 1 micron technology, what is the lambda associated with it? 0.5. If I have 0.5 micron technology, lambda associated with this 0.25. So suppose you have done a design using 1 micron technology, right? And you know technologies are continuously advancing. So after 2 years or whatever, 1 year and a half, you have a 0.5 micron technology available. And you want to design something. Now you don't have to design from scratch. Whatever designs you already have, what do you have to do? Instead of lambda equal to 0.5, just put lambda equal to 0.25 because very simple. So your design can be very easily migrated from one technology to the other technology. Why? Because I have a representation of my layout which is independent of technology, right? So this is very important. Now, why is it very important? As I've been saying, technology is changing rapidly. Circuit complexity is continuously increasing, right? And circuit complexity, which means that, every year and a half or 2 years, a new technology comes into view. And it allows you to pack more and more transistors, right? And therefore, as designers, when you go and join a company, you are asked to design more and more complex circuits in about the same time, right? So the amount of time that you have available for carrying out the design is not increasing, and the company is not hiring more and more engineers, right? So the demand on a designer is continuously increasing. Design more and more complex designs in the same amount of time. So how do you do that? Well, one of the ways that people do is, the design that people do is they don't do it from scratch. They use the concept of reuse. Reuse as much as possible of whatever you've done earlier. Designs that you've done earlier, reuse them. Now, how do you reuse them? If you have a new technology, how can you reuse a design which was done in a different technology? It's not straightforward unless you use the concept of technology independent representation. So there are 2 ways in which, let me illustrate, one can do a design. One is, I have a specs, right? Whatever I'm designing, and I go through a design process. And in my design process, all the technology information is embedded, and I get a design. So my design is, note, the final design is specific to the technology, right? Specific to the technology. Now, in this case, if I want to migrate my design from one process to the other process, I have to go through the whole process, the whole thing again. The second one, look at the second design. It has 2 steps into it. From the specs, you do a design, but you have an intermediate level design, which is technology independent. And then here is where a next step comes, where you add the technology information and it becomes technology specific. So when you go from one technology to the other technology, there's a part of a design which is already done. You only have to add the technology information, right? So lambda rules is one example. We have a part of the technology design which is already done. For us, it's very simple. If you want me to design for a new technology, all I have to do is technology information is lambda equal to 0.25 or lambda equal to 0.1. It's very simple here. Okay? But lambda rules are very simple, and I'll tell you in a minute why lambda rules are not suitable. People in actual industry will not use lambda rules. They will actually use the precise micron based rules here. Okay? And the reason is as follows here. Reason is as follows. Say I have 2 different technologies. Okay, this is a slightly abstract discussion. Two different technologies. Technologies are 1 micron and 0.5 micron. Okay. In that technology, 1 micron, and there are some feature sizes. Let's not worry about whether it's poly or diffusion or metal or whatever. Some feature sizes, they're L1, L2, L3. Technology 1 micron technology, the minimum size of L1 is 1 micron, minimum size of L2 is 10 micron, minimum size of L3 is 3 micron. Okay. Technology 2, which is 0.5 micron, minimum size of L1 is 0.5, L2 is 3 micron, L3 is 2 micron. So these are two technologies that exist, right? Okay. Now you have to come up with lambda rules. You have to come up with lambda rules, keeping in mind that these two technologies are there. Okay. How do we do that? Well, I do the following. First of all, I try to convert it into a lambda rule for each one. So I have 1 micron, I put lambda equal to 0.5. So in terms of lambda, it becomes 2 lambda, 20 lambda, 6 lambda. Right? Now for the second one, I have lambda equal to 0.25 and it becomes 2 lambda, 12 lambda and 8 lambda. Now I want one set of lambda rules which is applicable to both. Because that's the idea of lambda rules, right? You can easily grow from 0.5 to 0.25. All you have to do is just change lambda 1. So my rules have to be valid for all the technologies. What do I have to do? So what I will have to do is, I will have to choose something which is the worst case. So for first one, I choose 2 lambda. For the second one, 20 lambda. For the third one, 8 lambda here. So what you are seeing here is that lambda rules are very simple, but they represent the worst case scenario. In fact, when I'm using lambda rules, I'm not taking advantage of fully of the technology that is available. For example, if I just use lambda rules, now for L2, I'm going to use a feature size of 20 lambda, right? While actually the technology allows 12 lambda, right? So this is the trouble which is there. And lambda rules are very simple. They represent the worst case rules, and they'll always be valid. But you're not fully taking advantage of a technology which is there. The minimum feature size of different things that is allowed there. So it's very simplified, but not that good. And that's why in the industry they will not use these lambda rules. They will actually go and use the actual rules that are there in terms of actual microns. But then if you use, now let's go back then. If I do a design, if I do a layout with the actual rules, right? Then how do I migrate it to a different technology? A new technology comes in. How do I migrate it?
You just change dimensions according.
No, I have to go and redraw each of the rectangles, right? I have to redo the layout. Imagine you're doing a layout of a complete ADC or a circuit with 1,000 transistors. I have to sit down and redo all of that. That's a very time-consuming thing. My issue is, how do I get a technology-independent representation now? So my problem is, I want a technology-independent representation, right? You see the power of technology-independent representation. I don't have to do the whole thing from scratch. So for a layout, how do I get a technology-independent representation?
Instead of 2 lambda, 3 lambda, use 8 lambda, 3 lambda.
You say what?
Not use the coefficients.
Don't fix the size. If the coefficients, which means no size. See, if you're doing a layout and there is a size information in the layout, then it becomes technology specific. Because how do you decide on the size? It's the technology which decides the size. So if I want a technology independent representation, you realize that representation will not have any size information. Yeah.
Mostly we are working with angles and polys and also we recognize them as independent entities and then specify minimum quantities for each entity. So like we did, there was a minimum.
But these are changing from technology to technology, right?
So as what we do is we just specify the minimum size as lambda for each of these features. And then redraw the entire circuit in terms of lambda.
No, so you have to redo it. You have to redo the layout. You have to redo the layout. Layout has size information into it. You have to
if we represent it in terms of lambda poly, lambda well, lambda that, then all you have to do is just plug in the values of lambda.
For all of them, you'll have to rechange. You have to rechange, and plus you have to see, depending on the layout, it's not just the size of each one, but the shape may also change.
Interconnection.
They also change. My point is, if you want a technology independent layout, that layout, one way of looking at it is that layout cannot have any size information. Because if it has size information in it, then it becomes technology specific. Right? So I'm pointing out one possibility is stick layout. A layout which doesn't have any size information in it. All right, look at this. So here is a complete layout with all the sizes, all the rules, everything in it, right? And if you go to the left, this layout doesn't have any size information, right? It is technology independent. Instead of a metal, I draw it's called a stick because for various layers I have lines, right? I have a metal line here that you see here, metal line here. So this is VDD, this is ground, and this shows a this shows a N plus line here, and this shows a red one is a poly line here. This one is a poly line, a P plus here, and it shows the complete layer. At least it shows you all the structure of the layer, right? It doesn't have any size information. Doesn't have any size information. Is it useful? Is technology independent? Is technology independent? Is it useful? No.
So this is the same as the schematic.
No, it's not the same as schematic. It is not.
It's actually a bit easier to draw a new layout using this stick layout.
Okay, so this is also telling you is when you are thinking of doing a layout, right? Don't start immediately thinking in terms of a full-blown layout. What he's pointing out is it becomes easier to do a layout. What you do is first sketch a stick layout, and then once you have a stick layout, then you convert it here. But are you seeing something interesting? Once I have the stick layout, first of all, going from a stick layout to this layout, what kind of a process is it? It's a tedious process, agreed. But does it require a lot of thinking? Does it require? Because what does it require? See, for example, this line, it has to be 3 lines. There are certain set of rules that you have to follow, right? So, which means that if the process is not creative, if a process is very straightforward and mechanical, what can you do? You write a CAD tool. You write a CAD tool which will take this stick layout and will convert it to you. Convert this one to this one. So as a designer, then the issue as a designer is not how much is the size here and how much is the size here and all of that. The issue is what is the overall layout? What is the overall structure? Okay, and if you can fix that using a stick layout, then you can write a tool which will convert the stick layout into a full-blown layout. All right, that's one possibility. I'll show you whether this is useful or not. Think about this inverter. This is one way of conceptualizing an inverter that I said. Can you see something about this one? That if you do an inverter like this, its height is going to be large because you're stacking NMOSes and PMOSes together, and its width is going to be small. Remember, height was 3 times the width. But suppose you want a square layout. What will you do? Square layout. Squarish, more like 1 by 1. Is this the only way in which you will do the layout? I mean, this immediately follows from the schematic, right? You draw the schematic like this and you do exactly the same. But is this the only way you can do a layout? Now with the stick layout, you can come up with different ones. For example, why does it have to be vertical? Why can't you make it horizontal? Can I do this? Look at this one. W by L will be? In this? No, that information, in the stick layout, there's no information. Stick layout has only information about orientation of the transistors and the relative positions and all. There's a separate file which keeps all the information. That this transistor M1 is this much, this M2 is this much. And there's a file which will keep all the information about design rules, which are part of the technology. Right? So and there's a CAD tool which will take in all those information and convert that into a final layout. Okay, so all that information is embedded there. But stick layout has this, you can appreciate that this layout will be different from this layout. The two will be different. their aspect ratios will be different. Maybe the parasitics will be different. Okay. So the advantage is that the point is that some of the critical information in a layout you can capture in the form of a stick layout, and it's a technology independent representation. And then you use a CAD tool to add all the technology specific information and make a final layout. Okay. So what I'm trying to point out is the importance of technology independent representation. Stick layout is a very, very simplified version of that. Okay, technology independent representation, and the use of a CAD tool to add more mechanical technology specific information to get the final layout. For this class, of course you're not going to use any CAD tools and all that to convert a stick layout to a full layout. The advantage is that when you draw layouts of a more complicated differential pairs or a op-amp, stick layout will help you conceptualize. You can very quickly draw and look at the different ways in which you can make the layout using this particular picture. So for you, the advantage is very simple conceptualization of what the layout is. So you do it on paper, and then you actually go and do it using the software. Okay. All right. We have a few more minutes. So now in the remaining part, so we have done an NMOS, we have done a PMOS, we have seen how to connect them up. We know that parasitics are important. What I have to do is now look at resistors and capacitors. How do we make them? Okay. So a few slides on resistors and then I'll stop. Okay. So we know that in analog circuits, of course, I need resistors. So now the technologies that have been developed, they've been developed with the idea of making good NMOS and good PMOS transistors. These technologies are not very good for implementing the passive components. They've been developed with keeping in mind the transistors here. So making a resistor, for example, you'll just see becomes difficult. Making a capacitor also becomes difficult. And inductors are, of course, even more difficult here. So how do I make a resistor? Well, this shows you one way of doing it. I have an N-well, and in an N-well, what I can do is I can create a P plus layer. Right? P plus normal diffusion and all that is done. So I create a P plus layer here. All this is SiO2. I make a contact here. I make a contact. And in between the two, I have a resistor. Okay. Is it a good resistor now? How do I evaluate a resistor? What are the parameters that I use to evaluate a resistor? The first thing is sheet resistance. You'll see why. Note that resistance is equal to rho L by A, and rho L by A here. And this area, part of the area, I can take the thickness out. So area is thickness into width, thickness out, and rho divided by thickness is what we call as the sheet resistance. And sheet resistance multiplied by the length and the width of the resistor. Okay. So sheet resistance is important. And note that I'm using a P plus layer, as I said, to make a resistor. Now what will happen is, if the sheet resistance is small, then what will happen is L by W will become large. My resistor will occupy a very large area. Let me show you an example. The sheet resistance that I'm talking about, this one here, P plus, the sheet resistance is about 2 ohms per square. So which means that if you want to make a 100 kilo ohm resistor, if I choose the width equal to 1 micron, the length will become 10 to the power 4 micron. And the overall area of my resistor will become 10 to the power 4 micron square. It's a huge area. Imagine that if I'm making a transistor area is much, much smaller. So you are just seeing a 100 kilo ohm resistor will require a huge area to do. So what it is telling you is that this N plus region or P plus region is not very suitable. If you want to make a large resistor, it's not very suitable for doing that. I have to look for some other ways of making a resistor. This is just showing you a layout wise how you make a resistor here. Of course, if you have a resistor like this, you're not going to make width equal to 1 micron and L equal to 10 to the power 4 micron is how much? 10 to the power 4 micron is 1 centimeter, right? Your chip itself will be a millimeter. So you can't make this, right? You can't have a 1 micron width and a thin line running all the way. What will you do? Right? This is what you end up doing. Serpentine way, you go like this here. Now, what you see here is, so serpentine design, what you see here is, as the current flows, there's a nice current flow here, But at the corners, it becomes a problem. Corners is the current flow is more complicated. And it becomes difficult as a designer for you to predict how much will be the resistance here, because calculation of resistance around the corners is a little bit tedious. So what people do is many times they make a design like this. They go here, and at the corner they just put a metal here, metal shorts it, and then it's a nice flow of carriers here. Then they short it here, and then like this. Okay. So typically, in order to minimize, in order to keep a nice shape to your resistor, you don't make one long wire like this. Normally for most of the components that we do, or most of the layouts, we are normally aiming for a aspect ratio of close to 1. All right, because the final chip is also going to be 1 millimeter by 1 millimeter or 2 millimeter by 1. Okay, something of that sort. So that's why you don't do like this. You have to do a serpentine, and this is something that you can do. Now there are many things, many issues here. Sheet resistance is one. Temperature coefficient. Temperature coefficient is another important one. You don't want a resistor which varies the temperature. We'll go over it in the next lecture. Voltage coefficient. What do I mean by voltage coefficient? That as you change the voltage across the resistor, its value changes. Okay? You can see here. Look at this particular resistor. Can you see why its voltage, as you change the voltage, the value of the resistance will change? See, there's a P plus here, there's an N well here, there's a little bit of depletion region in the P also. As you change the voltage between the two resistors, the amount of depletion width will change, and therefore the resistivity of this particular resistivity remains the same, but the effective thickness changes, and so sheet resistance changes. And therefore, the resistors have a voltage coefficient. Right? So you have to worry about the sheet resistance. You would like sheet resistance to be large so that the area occupied by a resistor is small. You would like temperature coefficient to be small. You would like voltage coefficient to be small. And what else do you see? You don't get a resistor. Between P plus and N, what do you get? A capacitance. So you're getting a capacitance. You don't think of it as a bonus that, in addition to resistor, you get a capacitor. You don't want a capacitor. Right? So you're getting all these parasitic capacitances. So you're seeing that when I'm trying to make a simple resistor, you're having all these problems that are there. The technology is not built for making resistors. Okay, that's why in all of this design, we try to minimize use of resistors. Okay, so we'll discuss, let me stop. I can see all of you are tired. So instead of going forward, let me stop here, and one can take some